Hello, welcome to a concept session. So we are going to talk about polar coordinates today, and they are very useful and kind of very important when you're dealing with motion in the plane. So suppose motion is happening in XY plane. So we're just going to say motion in XY plane. So XY plane doesn't have to be like this. It can be like this. So it can be like that. So it can be oriented any which way, as long as the object is just moving in this plane or just moving confined to that plane, So as long as confined to a plane. So we will call any one of these, whatever the confinement of the motion is. If it's as long as it's confined in a physical plane, we just call that plane XY plane. Okay. So let's take this XY plane. So x-axis this going to the right, and y-axis to the left. So we're just looking at the plane from above. Okay. An object is, say, at this instant at time t, it's over here. It may be moving around. It may be it's going around, maybe in a circle, what have you. So it's going around, and it's over here right now. So the position vector. So the position vector is this, and we denote r as a position vector. So this is a position vector, and this is a function of time. So it's moving at different time. Sometime before the position vector are pointed over here, sometimes it is pointed over here, sometimes it's pointed over here. So this is changing in time. Vector is pointed at different time and at different distance. The magnitude of this vector, magnitude, we denote by just letter r. So this distance from origin to here is letter r. And the because this is in a plane, for direction, we just use this angle for the direction. So magnitude this in the direction denoted by this angle with respect to positive x-axis, angle theta. These r and theta are called polar coordinates. R and theta are polar coordinates. So we want to we can see that r can be a function of time. So r is a function of time, and theta is also a function of time, because over here theta was 0, over here theta is some non-zero value, when it's over here theta is some other value. So these are the functions of time. So when we talk about kinematics in polar coordinates, we mean look at the position vector and try to describe the motion in terms of its magnitude and its direction as it changes in time. So we learned how to describe the position vector by another way. Use the coordinate x and y, and these are functions of time. These are functions of time, and we use this unit vector I hat towards the positive x-axis and unit vector along that direction j hat. So we can write any vector. So we learn how to write r vector, which is a function of time, as x time I hat. So made up this x I hat and this projection, and this was the y j hat. So just adding these two vectors gives you the r vector plus y of t j hat. Now if you look at I hat and j hat, no matter where this particle is, if I if I do x and y coordinates over here, x and y, I hat is still this way and j hat is still this way. So I hat and j hat constant in time. I hat always points towards this direction and j hat always points to this direction, and their magnitude is 1 and they don't have any units. All right, so they always point in the same direction in time. So if I were to say how about will have, if I take a derivative I hat, that should be 0. If I take a derivative of j hat with time, that should also be 0. So these are kind of special vectors, constant vectors. And if one would say what's the velocity at this instant, we'll just take a derivative of that, right? So let me erase some of that. Okay, so the velocity vector, you can see I can already say dr dt, that's the velocity at this instant. And when I go out and take a derivative, d dt of this whole thing, that should distribute as d dt of x I hat j hat, right? Okay, then this is a product, so you can do two terms here, dx dt I hat plus xt d I hat dt plus a similar thing over here. This will be 0 because I hat doesn't change with time, so I have got dx dt I hat, and from this you get a dy dt j hat. And we can write this as these are components, dx dt dy dt, which is the same as vx vy. Now this is how we did before. How can we write things in terms of r and theta? That's the question. Okay, so I think we can do it. We can keep I hat and j hat, and we can see that in this this distance is x and this distance is y from the xy. So you can already see that x equals to r cosine theta from this triangle, and y equals to r sine theta. Or if you want to go other way around, r will be square root of x square plus y square. This is always positive, so the r, unlike x and y, that r can always be positive. So r can be r has to be like this. X is minus infinity like that, and y is similarly, and theta is 0 to 2 pi, right? It can only be in direction can be between 0 and 2 pi. You can say like this, just to include both these points and identify 2 pi direction is the same as 0. All right, you can see it will we can use this in r, and in that case I'll get an r vector. Let me erase and write some parallel. So this r vector, I can just substitute for x r cosine theta. So this will be r, which is a function of time, cosine theta, which is a function of time. So this will be I hat, r, which is a function of time, sine theta, which is a function of time, j hat. So I don't have to do anything more than this. We can use our this I hat and J hat as before. So that's one way of doing it. And what we will do in just a little while is write in terms of some other directions, and we'll see the directions in just a minute. But just let's look at how far we can go while keeping direction I hat and J hat. And often this is very useful. Just that's why I'm doing it. So if I go in the velocity, so the velocity will be when I carry this out, when I have a velocity is equal to dr dt, we already know that there will be derivative of the x and I hat, and then you carry all the way here, and then it's just going to turn out to be dRt cosine theta of t O of dt, and this will be I hat, and similarly for that side. Now you can see this is going to be pretty messy, and I'm going to say dot, use dot for ddt. Then this will spread out, and this, you can have a r dot cosine theta minus r minus theta dot r theta dot sine theta I hat, plus I'm going to do dot of this guy. I've got r dot sine theta plus r theta dot cosine theta j hat. So that's going to be velocity, and it's going to have, instead of like a so that's a v sub x, and this is v sub y, but it's written using r and theta. So that's sometimes useful, okay? And it's a problem dependent, but if you are not really comfortable with doing this, you will miss it, because when there's a problem, you say, okay, I could think I hat and J hat, but I would use R and theta because the problem is simpler when I'm thinking in terms of R and theta. Then this direction of calculation sometimes is very helpful, okay? So R dot here, just to remind you, so R dot is dr dt, and theta dot is d theta dt. Similarly, we can have x dot equals dx dt, y dot is dy dt. And let me clean this up and do the acceleration quickly, okay? Okay, so I went ahead and did the calculation for the acceleration, and you can see that I just have to take the time derivative of this, and so from the first line, just with the Cartesian, it's just simply this. Now again, I had to use this because each of these terms, if you look ddt of x dot I hat, you're going to distribute, and you're going to have dx dot dt I hat plus x dot di hat dt. Now this is 0, and this is just x double dot. That's just x double dot I, and this is I hat. So that's where the first term comes. Now if I do this ddt of this stuff, having experienced that that guy will be killed, I just have to do the ddt of that guy. And so I do it looking forward to both terms, things coming from both terms. So r double dot, that's the first one, remaining this same. And then when I take a derivative of this, I generate one of these, but when I take a r dot, I generate another one. That's why I got a 2 here. And then I go theta, I generate this term. I do sine theta, generate that term. And similarly, you can do this one, okay? So it's pretty complicated. Often we may be interested in uniform circular motion. So uniform circular motion. Okay, in the uniform circular motion, what's going on? R equals to constant. That's one case. And the second condition is that this theta in equal time is going to move at the same pace. It's like a theta dot equals to constant. So this will mean R dot is 0 and R double dot is 0. And this will mean theta double dot is 0. So if you put these conditions in these guys, then the velocity will simply become, you can see R dot is 0. It's going to be minus R theta dot sine theta I hat and plus R theta dot cosine theta j hat. But R sine theta, so you can write in a mixed one, this one, a very nice way. So this can be y theta dot I hat plus x theta dot j hat. So it's like you can take a theta dot outside and can say minus y I hat plus x j hat. Like x and y kind of changed in that. So v is this is a mixed, and sometimes can be useful in a problem. How about acceleration? If I do, this is 0, this is 0, this is 0, this is not 0. So I have a minus r theta dot square cosine theta I hat, and this is 0, this is 0, this is 0, and so this is minus r theta dot square sine theta j hat. And so this is basically what's going on is theta. If I look at theta dot square as a common, minus theta dot square common, then I have x I hat plus y j hat, which is simply the vector r. So minus theta dot square vector r. So acceleration is opposite to the vector r in this case. So if you have uniform circular motion and the particle is over here, this is the r vector that way, from the origin to that, that's the r vector. Then the acceleration is, you've probably seen this before somewhere. So acceleration is exactly to the center. And that's the case for uniform circular motion when these conditions apply. So this is a very calculational way of seeing this, and there's no, there's nothing hidden here. Every step is kind of very clear. There is another way, and a little bit more advanced way to think about polar coordinates. And that turns out to be, in place of I hat and j hat, we introduce something called polar unit vectors. Okay, so the unit vectors are here, I hat and j hat, and we can introduce two new vectors in this plane. One is going to be in this direction, because you can see our vector is very important. So we can say what a unit vector in that direction, when it's over here, we just call it, sometimes we just call it r hat. Sometimes we call it u hat r, couple of names for unit vector. So r hat is if I'm point P, then r hat is pointed that way. If I'm over here, r hat is pointed that way. So let's call it q. R hat when I'm at q. So this r hat at point P. So it's r hat. So these guys come with a label attached to where I am. Okay, or which direction I am, and you will see that it doesn't depend on how far you are, but only depends on theta. We will see that. So r hat attached to theta, theta corresponding to point P, this theta corresponding to point Q. Okay, so this is r hat. That's going to be vector from the O in that away from the origin. Okay, and then I need one more vector perpendicular to this, and that's 90 degrees, and in our fashion we go 90 degree clockwise. So we got 90 degree counterclockwise. So we have another unit vector. We can call it theta hat, or theta hat associated with that direction theta at P. And I'm not going to use all this labeling, simplify and later, or you just call U hat theta. So I'm going to clean it up, and instead of writing all these quantities in terms of this I hat and j hat, we'll start to have these special vectors, unit vectors in the polar coordinates. And let's try to do that. Okay, so far we've done what is called mixed way of doing polar coordinates, where you use both this I hat along this direction and j hat along that direction. So use x and y sometimes, and use r and theta sometimes. That's called mixed one, right? But there's a way where you don't have to really use x and y, and you can write everything in r theta, and instead of using this Cartesian constant unit vectors, you can use unit vectors based on this position vector. So unit vectors, these are vectors based on direction of position vector r. So we imagine that from O, and this is where the object is, this is the position vector, and we imagine that there is a unit vector in that direction. So that unit vector we're going to label, because of going in r direction, we can label with, say, r hat, just like I hat. It should have been x hat, but people write I hat. So you can write r hat, or you can write, or you can say u hat r, just to another notation like that. So that's the one vector. One is unit vector in direction of r. That just means if r hat will simply be take my position vector, divide by its magnitude. Well, what's the magnitude? Magnitude is going to be just r, the distance which we write label r. So this would be equal to, and this one is just r cosine theta times I hat plus r sine theta j hat over r. And you can say r got cancelled out. So r hat and I hat and j hat are connected like this: cosine theta I hat plus sine theta j hat. It's vector in that direction. But you can say, hey, you're cheating, this is also mixed. That's true, you are never going to be able to completely get rid of I hat and j hat in your thinking, because you have to tell exactly what direction it is in space, right? So you want to describe that with respect to the coordinate system. The coordinate system will come with this x and y, and then we actually use radial coordinate, but then where you can do theta refers to the x direction, so you never really get rid of I hat and j hat. Now the second vector that I want, so I want to replace these use of these two vectors, then I need two vectors also. So normally you want another vector that's independent of the direction of r hat, and you want, the normal thing to do is get it in the 90 degrees, and the convention is in the direction of increasing theta. So theta is increasing that way. So you that's counterclockwise, right? So increasing theta, and when I'm over here, I seek a unit vector which is 90 degrees to the direction of r hat, and we have only other symbol, so to denote that's a theta hat, so we're going to call it theta hat. So if you do that, you can show that theta hat, if you just rotate this 90 degrees, so this direction, you had a direction vector like this, and you rotate 90 degrees, you can just put here theta, so theta plus pi over 2, that cosine of this I hat plus sine theta plus pi over 2 j hat, and you can expand this and you can just see what this will be. Cosine, it will become sine theta minus sine theta I hat, and this will become simply sine pi over 2 cosine theta, so this is going to be cosine theta j hat. Now you can already see that say this object was moving around like that, then its theta is changing. It used to be over here, that used to be here, now it's over here, so theta is changing. So theta is a function of time. So unlike I hat and j hat, this r hat will be a function of time, since theta is a function of time. Similarly, theta hat will be a function of time since theta is a function of time. Now this hat is to distinguish between the different quantities, right? So hat is a vector, it's a unit vector, and theta itself is just one number, just a real number. Okay, so how do we write down kinematic quantities in terms of these vectors? Okay, using these vectors, and that's pretty really interesting. All right, so you will see right away that if I want to r, right from here, I already know that this very simple expression r hat. This is because denominator is just radial distance r, right? And if I want to do a velocity, which is take a time derivative of this, I want to do velocity will be take a time derivative of this vector, then I got product rule there. So, and I'm going to use dot for d over dt. This saves a lot of time when I'm working with a whole bunch of symbols. And r hat dot. Now we got this. This is not either r hat or theta hat. It's a vector. So I need to figure out what that will be. So I go out there and say, okay, if I take a time derivative of this, what do I get? So when you do time derivative of this, when you do time r hat dot, you will get a theta dot from here and theta dot from here. So theta dot and could be common, and this will become minus sine theta I hat, and that becomes cosine theta j hat. But that's just theta hat. So this whole thing is just theta hat. So this is theta dot theta hat. So this velocity vector, in just using r hat and theta hat, will be r dot r hat plus r theta dot theta hat. Okay, now you can see you can actually carry this through and do acceleration, which I'm going to erase some of this and try to show you what the answer is. Okay, so acceleration, I worked out the acceleration. Just plug this for velocity in here and distribute ddt and use dot notation. And here is a little thing I left out for you to do using theta hat is simply minus sine theta I hat plus cosine theta j hat, using this we worked out earlier. And then you get little complicated experimental acceleration, but a little bit less complicated looking than the one we had for when you use just I hat and j hat. So you can do in a special case, just like we did before, uniform circular motion. So in this case, what are we going to have? We're going to have r will be constant, some radius, right? So it's going on some radius r, and we have theta dot is going covering same angle, same distance, equals to constant. So when we work this out, r double dot will be 0. So this will mean r dot, r double dot, all those are 0, and this just means theta dot double dot is 0. So in this case, you can get r hat minus r theta dot square, and this thing is 0. So it actually shows you very nicely that this is the acceleration, and put minus with the r direction, so minus r hat direction and r theta dot square. Sometimes theta dot is denoted by letter omega, and this angular velocity. So you have r omega square, radius times this, when you work it like that. So this is the acceleration pointed radially in, and that's the so this is centripetal acceleration. It's very easy to see in this coordinate system. You have to pay a little bit of price for doing all this more algebra later on, but you can see uniform circular motion works out very nicely when I use appropriate polar coordinate, right? But if suppose I don't have a circular motion, maybe I have a not circle but elliptical motion. Even there, it will be easier to work out polar coordinates. Okay, but you'll have to you won't have this the case, and you won't have this the case. But you for elliptical motion, your angular momentum will be conserved. Okay, so there would be some ways to simplify things. However, this is just wanted to make sure that you have some basics already covered before we get into more advanced topics and do more problems. So this is it for now. We're gonna talk more about these things in the coming weeks. So talk to you later. Bye.